Okay, so for 12-2, chords and arcs, we first have to know what a chord is, and not a musical chord, but a chord in a circle. So it's a segment in a circle that's not a radius or diameter, whose endpoints are on the circle. So you can see I drew a chord right here. Both of its endpoints are on the circle, okay, and it doesn't go through the center. So we label that as a chord. So it's really any line in a circle that doesn't go through the center, okay? Its endpoints have to be on the circle. That's what makes the segment. It has two endpoints. Now we have three theorems that go along with chords and arcs. So this first one, it's worded a little weird, but within a circle or congruent circles, congruent central angles, so that's angles that are based on the center, have congruent arcs, so that's arc AB and CD, which is pretty obvious. Remember, arc measure is based off of central angle, so if they have the same central angle, they're going to have the same arc measure. And then we're introducing kind of a new concept. They also have congruent chords. Okay, so the chord from A to B and the chord from C to D is congruent. Now, this is why when naming things, it is so very important to actually use their names or the symbols. So angle, AOB, COD, arc, AB and CD, notice the little arc marks, and segment, so chord has endpoints on the circle, AB and CD, okay? That's why it's so important. If you're naming these and you don't have the ability, like if you're typing them on a computer, and you don't have the ability to do the arcs and the dashes, you should type arc AB and arc CD and chord AB and chord CD, okay? When you don't have the ability to put the symbols on there, type it out. Okay, this concept is pretty easy for the second theorem. If two chords are equidistant, that's equal distance from the center, then they are congruent, okay? So distance, so we have two chords right here, AB and CD. Distance, the fastest way from a point to a line is perpendicular to it. So it ends up forming a right angle. So this distance is the same. That means that the chord lengths are going to be the same. So if OE is congruent to OF, then AB is congruent to CD. Now this works backwards too, okay? Works backwards too. If the chords are congruent, they're equally distanced to the center. It's very important, okay? And the last theorem is also very important. If a diameter is perpendicular to a chord, then it bisects the chord and its arc. Okay, so a diameter or a radius, really, the requirement is that it goes through the center. So if it's perpendicular to the chord, it cuts it in half, and it cuts the arc in half. Okay, and it works in reverse too. If the arc and chord are cut in half, then this is a right angle. It's perpendicular. And we can use those right angles to solve problems such as draw a radius right here from C to O. That's a radius. I can use the Pythagorean theorem here. And I'm going to show you that in an example here. Okay. So my first example is based off the first theorem. Zoom in. And really, if one of these is true, all of these is true. So if any one of these things are true, the other two are true as well. So it's given that the chords are congruent. Chord BC is congruent to chord DF. So we can also say that the central angles are congruent, angle BOC and angle DPF. But we can also say the arcs are congruent, arc BC and arc DF. Okay? Using the second theorem, we can also see, let me focus that. We can see this 9 is related to this distance from O to the chord. So from center to the chord, both of those are 9. And it's perpendicular, so we know it's cutting the chord perfectly in half. So that kind of goes with both of the last two. Okay, but I also know that the chords are going to be congruent. So if this is 12.5, I know this whole thing is 25. And so this whole thing, RS, is going to be 25. It really is that easy. Try not to overthink it. Like, you just say that's 12.5 for that dash mark. 12.5 times 2 is 25. So the other chord is 25 because they're equally distanced. The last example problem, up here. We have a radius or diameter. Now, if I would have extended that, you would be able to tell it's a radius or diameter a lot easier. But the point is that it's going from the center to an edge. Okay, it's perpendicular to this chord LM, which means that the right angle is formed. That also means that it cuts this in half. So I know that this part's going to be 7 and this part's going to be 7. Well, then I have a right triangle with a 3, 7, and a missing hypotenuse. I can do the Pythagorean theorem to find the measure of that missing hypotenuse, which happens to be the radius. Now, we can do the exact same thing here, but it's going to show a problem, and that's not going to be drawn. It's going to show a radius like over here, and you're like, I don't know how to solve this problem. The radius is the same all the way around. So if it gives you a radius of 15, that means the length from A to B is 15 because that's a radius. So once again, this is cut in half, so I know this is a right angle. So then I can just do the Pythagorean theorem. Y squared plus 11 squared equals 15 squared. Okay? You're going to be using the Pythagorean theorem a lot in this chapter. The key thing is remembering right angles and that the radius is the same all the way around the circle. It's also the same in congruent circles. So if you have two circles that are congruent, the radius is going to be the same in both. So keep that in mind while working on 12-2, chords and arcs.